Before the break, I was sort of talking about should we follow thought leaders or should we try to measure preferences. And one thought leader could be Johnny Rotten, right? And a lot of people have followed what he's been saying. And nowadays he says two things, right? One is buy more butter, and the other thing that he used to say is it's better to burn out than to fade away, which is a very clear statement about time preference. That you should live as intensely as you can and then die, right? Now we can follow Johnny's advice there and sort of take his word as given. If you actually look at how he's living his life, right, he's clearly fading away, right? He seems to have not followed his own advice. So perhaps we should try and measure these things rather and look at people, how people live their lives rather than what they say about how they should be living their life. So if we take that and we sort of like assume a democratic standpoint that we should follow the advice of our electorate rather than try and impose our will on them, we would need to try and measure people's attitudes towards time, risk, and others. And the question then is, of course, how, right? And that's what I'm going to talk about in this final hour. You guys, of course, have 12 more to go with stable. So let's start with risk. So we go back to Van Neumann Morgenstern and we ask what is the value of a lottery, then the answer is here, right? The value of a lottery V, lottery L, is we win the lottery and we win the amount D, then the amount of money that we have would go up by that, so that enters into our utility function, and then the probability of that occurring is this. So we take the weighted average, we take the expected utility that we see there, and then of course we have to subtract the utility in the base state when we did not enter the lottery, and that is minus UC, and that is the value of welfare increase that we gain from the expected welfare increase that we gain from entering into this lottery. And then if we assume a CRRA utility function, then U becomes C over 1 to the power minus 8 over 1 minus 8, so we take 1 minus 8 to the other side of the equation, and we get this expression here, right? And the more recent development due to Kahneman and Tversky, which is sort of the common way of doing things nowadays, we sort of go and say, no, the value of a lottery is really some sort of welfare function. The prospect that we're looking at has some function W of the payoff times the probability of that payoff. We add it all up, and that is really what we should be looking at. There's some sort of reserve point there R, and then typically what people do is that they say that this sort of function W is a power function, so we raise D minus R to the power E, or epsilon, sorry, and this is the value of a lottery. And then as soon as you take it to the data, people rapidly discover that different people have different risk sensitivities. This is risk aversion in the proper Alfred sense of the word. This is the risk sensitivity parameter. What people immediately find is that people at different incomes value the prospects of different lotteries differently, which follows immediately if what is at stake in the lottery is 1,000 euros, then somebody on a low income, like a student, would think 1,000 euros is quite a big win, whereas somebody who is an investment banker would probably think that 1,000 euros is peanuts, right? So the people at different income levels would respond differently to the prospect of winning 1,000 euros. And then what you need to do is make the risk sensitivity a function of the base income. Now Kahneman won the Nobel Prize for this stuff. Tversky didn't because he died before. I really don't see this. I really don't see why this particular function is better than this particular function. Here you have the income dependence built in based on first principles. Here you add it on ad hoc. Both assume some sort of power function. With all due respect, I don't think that Kahneman really improved on von Neumann Morgenstern in any substantial way in this regard. And of course, throwing in another Nobel laureate, for Simon, would immediately suggest that this function here will tell you that if D is small relative to C, that is, somebody is on an income of €1 million a year, and you ask them to play lottery for €1, they're not going to pay attention, right? This is not interesting to them. So if D is small to C, then the value of the lottery is basically nil. And this would immediately tell you that, whereas Kahneman-Tversky would not immediately tell you that. This would sort of suggest that playing for pennies when you're very rich is still something that you would want to do. So that's first bit of theory, right? How would you bring this to people, right? And you could look at how people behave in real lotteries. Data for that is very confidential. You can also set up surveys and put people into hypothetical lotteries, or you can put people in the lab and let them play lotteries and see what choices they make, and then actually pay them. Now, this is from a survey that I forgot to announce. I put it quietly on Blackboard. None of you seem to have noticed, or those who noticed seem to have ignored, right? So you can actually, as a bit of homework, display these things and see what is whether this works for you, right? But what you can ask are questions as follows, right? So there's 2 lotteries decided by the throw of a dice. In lottery 1, you'll win £100 or £1,000 or £2,000, and you'll win the £1,000 if we roll the dice and the dice falls on 1, 2, or 3, and if not, it falls on 4, 5, and 6. You'll win the £2,000, right? That is one lottery. Very clear prospect, right? 1,000 or 2,000, there's a chance of 1/2 or winning each. The dice is unbiased, so your expected payoff is 1,500. And then in lottery 2, you'll either win £600 or you'll win a larger amount. You'll win the 600 if the dice falls on 1, 2, 5, and you'll win the larger amount if the dice falls on 6. And then we vary the larger amount and see what lottery would you prefer. So the first larger amount is 6,000, right? So you have the chance of 5 out of 6 to win 600, so the expected payoff is 500. And you have a chance of 1 in 6 to win 6,000, so the expected payoff is 1,000. So together that makes 1,500. Same here, 1,500. So you should be indifferent between the two if you are risk neutral. If you are risk averse, you should prefer this one, because it's the lower, the smaller stakes. And then we increase these numbers in steps that are easy to calculate, and at one point people switch to and say, well, if the stake is 9,000, right, then I would really go for the riskier bet. I take for granted that I have a big chance of winning a little bit of money, but the prospect of winning a lot of money becomes very attractive to me, and I switch. The reason that you ask people to choose between 2 uncertain prospects is that some people are biased towards the sure thing, right? That they say, I don't care about lotteries, or maybe they have read the Quran, which says that you're not allowed to gamble, and they follow that guidance, right? And they say, I'm not going to do that. So by asking people to choose between 2 lotteries, you sort of avoid the bias towards sure thing. So that's what you can do, right? So if somebody accepts lottery 2 for 6,000, then 2 options there must be risk neutral or maybe even risk loving. And then the other ones, you need to throw in the base income. If you follow von Neumann Morgenstern, if somebody on an income of 29,000 a year rejects lottery 2 for 6,600, then we have an upper bound on a risk aversion of 1.4. The 1.4 is not true. So if at the same time she accepted the lottery for 66 but rejected the lottery for 60, then a risk aversion must lie between risk neutrality of 0 and risk aversion of 1.4, right? And that then follows. You can do this for a large number of people and then draw a probability density function of the risk aversion, which doesn't look at all what you would expect, right? I mean, typically what we do in economics is set the risk aversion equal to 1. And setting the risk aversion equal to 1 is very handy, because then your CRA becomes a log and everything is nice and smooth, and the mathematics becomes very easy. And one thing you can draw from this graph is that very few people seem to have a risk aversion that equals 1. There's a lot of people with high risk aversions, much higher risk aversions, and this of course also comes out of the equity premium puzzle literature. Risk aversion seems to be a lot higher than we traditionally assumed, but whenever you're running something with real people, you also find very peculiar behavior, and we actually find almost a third of the respondents expressing risk neutrality, or perhaps even risk loving, but of course us being silly economists, we did not allow them to express a love for risk. We just assumed that risk neutrality was the lower bound. So that sort of works in a simple way, but there's complications there. And one complication is risk amplification and risk suppression. What you're looking at on this axis is the objective risk, the probability of dying from botulism, while giving birth, from being struck by lightning, from dying of a stroke, from dying from heart disease, right? I think this is US data. On the vertical axis, you're looking at what happens, what is the answer that you get if you ask people what is the chance of dying from botulism or from a firework accident. If people were perfectly well informed, if they actually knew the risk of death of various things, they would be on the 45 degrees line. You see it dotted. And what you see is that people dramatically overestimate the small risks. They think that the small risks are much larger than they actually are, and the chance of dying of botulism in the US or in the Netherlands for that matter, really, really tiny. Give that a very large probability, whereas the chance of dying from heart disease is actually much larger than people, or is actually much larger than people think it is. People don't know the probability of things happening to them. They just have a lack of knowledge and they have a lack of understanding. Prelats introduced a fairly general form of doing this, where essentially rather than sticking in P, you stick a complicated transformation, back transformation, log X in there, and then you put a alpha in there. And if I'm not mistaken, if alpha is positive, then you overemphasize the small risk and underemphasize the large risks. So if people are like that, then they can't deal with objective probabilities, but somehow transform those probabilities in their head so that they overemphasize expected risk, then the interpretation of a thing like this becomes different, right? Because you need to process in, you need to take account that people don't do 1/2 versus 1/2, 5/6 versus 1/6, but they do something else. They, if you believe prelates, they underemphasize the 1/6 probability of winning, and if you don't account for that, then your estimate of their risk aversion is wrong, because you think they work with a probability of 1/6, but in their heads they work with a probability that is higher than 1/6, right? So you can throw in that, and that of course means that you need to be, if you do a simple choice between two lotteries, you need to be very careful in the way you interpret things. And if you want to measure this, then of course you should throw in additional observations, because there is an additional parameter to be estimated, right? You're no longer just estimating the risk sensitivity parameter epsilon, but you're now also estimating the risk amplification parameter alpha. So you need more observations and you need a cleverer design of your experiment. Kahneman and Tversky also noticed loss aversion, and we talked about loss aversion in the context of willingness to pay versus willingness to accept compensation, right? That people value losses differently than gains, even if the amount is the same. And then instead of having the D there, you would have D or minus D if D is negative, both raised to the same risk sensitivity parameter epsilon, but here we have a loss aversion amplification factor lambda. But lambda, if lambda is 1, the two are just the same, right? Whereas if lambda is greater than 1, then people would respond more strongly to prospective losses than they respond to prospective gains, right? And if you believe this, then of course you have 3 parameters to estimate, and your design of your experiment becomes more complicated still, right? And definitely you need more observations because you have more parameters to estimate. Loss aversion is very hard to estimate in the lab because you cannot go into the lab and take things away from your subjects. The ethical board would not give you permission, and the students would revolt if you try, right? Come, let me do an experiment with you, and as a result you'll walk out $10, $20, $30 poorer. No, right? They will not come if that is the case. So you need to be careful. You first need to give them the money and then take it away again. Okay, but it's relatively clear how this works and some of the complications that can happen. Time preference, very similar story. What we're looking at here are 3 different discount factors. In blue, we're looking at your standard geometric or exponential discounting. In green, we're looking at the hyperbolic discounting that I talked about yesterday, where you see that you come down faster in the beginning and then you flatten out. And I did not talk about present bias, which is a bit the same as sure thing bias, that it sometimes is the case that people just prefer things now, but then when you talk about trade-offs between a point in the future and a different point in the future, their discounting becomes geometric again, which follows, which is seen more easily if I transform the axis to a logarithmic scale. So present geometric discounting, you just go to a straight line in log space. Present bias, you jump in the first period and then go on a straight line that is parallel to the previous one. And then hyperbolic, you're actually not on a straight line in log space. So you need to take these things into account, and even though as economists we used to assume that discounting was geometric, it turns out that that is not the case, and you need to take this into account if you're trying to estimate these things. Benedict, Bizin, and Scholler came up with this fairly general discount function that is given here, that the discount factor, is beta times 1 minus theta RT to the power 1 over 1 minus theta. And the good thing about this thing, well, the bad thing is that it's just a mouthful, right? Like, what is this doing? And it's just hard to interpret. The good thing is that your standard forms of discounting all have an immediate, or are all special cases of this generalized function. So your present bias is essentially your beta, and then hyperbolicity follows if beta is 1 and theta is 2. Geometricity follows if beta and theta is 1. If theta is 1 but beta is smaller than 1, then your geometric with present bias. And of course you can also combine hyperbolicity with present bias. So what you then need to do in an experiment or in a survey or something is let people make these choices, right? Would you rather have £5 today or £1,000 in 6 years' time? A very large discount rate. Or would you be happy, would you rather have £950 today or £1,000 in 6 years' time? It's a very low discount rate. And then people with an intermediate discount rate would say no to the low payouts now and at a certain point switch over. Right? Now, if you want to estimate something complicated like the BBS discount factor with the three parameters, then you need to ask this question a number of times, right? With different switching points, a year from now versus 6 years from now, a year from now versus 2 years from now, today versus 5 years from now, today, and that's the top one that you can't see today versus a year from now. And you need sort of to shift the near future by a couple of times to sort of make a distinction between hyperbolicity and what some people call quasi-hyperbolicity, but what is better called present bias. Right? You can do that, and you would find discount rates that perhaps surprise you. So if we just focus on the blue for a bit, you see that a lot of people use extremely high discount rates. People use discount rates of more than 100%. This is if you ask people, what is your discount rate? Then they must be extremely capital constrained, right, to say this. Other people use discount rates that are closer to what they would actually get if they put their money in the bank or if they get a mortgage. And there's also people who use a very low discount rate. Now, some of this, once you start doing this, is just noise in the survey. So if you go from the blue to the yellow, essentially what happened there is because you ask the question in an open format, the rational person would say no, 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 yes, 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 yes. If you do this in an actual survey, you also have people say no, yes, no, yes, no, yes. Either because they don't understand the question or because they cannot be bothered to answer. So if you start throwing out those sort of people, you go from the blue to the yellow. Then in this particular survey, there were also questions about, do you understand the discount rate? Right? Not do you understand the discount rate? The obvious answer to that question is yes. Where you actually ask the question, suppose that you put your money in the bank, you have an interest rate of 2% per year, you get the money back after 2 years. Would you get more than 102 or less than 102 after the 2 years? And you'd be amazed at the amount of people who do not get that question correct, right? Who do not understand that in the first year you get 2%, and in the second year you get 2% again, plus 2% on the 2%. So you actually get way more than the 2%, right? A lot of people who don't understand this, then you take away some of the nonsense here, you take away some of the nonsense here, and then the survey also had questions about, can you do basic arithmetic? Not can you do basic arithmetic? Of course I can. No, actually solve this sum, right? You actually get the right answer. And then you take away some of the nonsense again. But you sort of begin to feel the complexity here. You also still see, if you focus on the red, where you sort of like filtered out all the nonsense, you still get fairly high discount rates if you ask the people rather than their religious leaders. When you ask those 4 questions, you can also classify people, and the ones who are geometric discounters sort of give a, regardless of how you ask the question, they always say 5%, right? They make up, in this particular case, only 12% of the population. 43% shows present bias, that is, that here and now is just dominates everything, but after that we go back to geometric discounting. 8% show hyperbolicity, that they discount less as the time horizon expands. 25% show both present bias and hyperbolicity, which sort of like puts faith to the standard economic assumption that everyone is a geometric discounter. It just doesn't help. Only 11% were the ones who just gave rubbish answer. And then there was 1% that he could not classify as either geometric or present bias or something, right? But the present bias seemed to be particularly strong. Also, if you don't explicitly account for present bias, then you may easily mistake the answers that you see as hyperbolic, right? You could be very careful there. Final thing, how do you measure inequity aversion? This is actually in the literature the least developed preference parameter or the measurement of parameter. And there's two things in the literature, and there's fairness and there is what I here call equity, but I'm not 100% sure that that is the right terminology. So there's been now a lot of literature on fairness, and essentially what the literature is about is I give a reward, a windfall to a group of people, how are they going to split it up amongst themselves? And there's a ton of experiments on that, which is a completely different question to the question, what is the optimal income distribution in the population? They're completely unrelated to each other. This is easy to measure, this is the question you want an answer to. And people have focused on the easy question and avoided the hard question. For the fairness, what you essentially do is you let people play dictator game. Dictator games works as follows. I give you £10 and then you have to divide that £10 between yourself and somebody else. And that somebody else has no sanction over you whatsoever, you don't know who they are. I gave you £10, how much of that £10 do you keep and how much do you give to your unknown neighbor? And strikingly, people give money to their neighbor. So the way to set this up is something as follows. You and Anne have won a prize. Which prize would you like best? The prize is the windfall, right? This is not money that you worked for. This is something that falls from the sky. Which prize would you like best? That you win £100 and Anne wins 50, or that you win 85 and Anne wins 15. So what you can do here is essentially test for masochism. Because you can really hurt Anne, but at the expense of hurting yourself. Surprisingly, there's people who go here, right? People, you can't argue with people's choices, right? That's what they want. I mean, some people like pain, some people like inflicting pain. Whereas here there is very clearly a trade-off, right? I mean, you can give up some of your money, but then Anne would get a lot more. And of course, if you and Anne are brother and sister or husband and wife, then this would be the logical thing, right? If you're sort of an harmonious relationship, because this maximizes the maximum, right? And this maximizes the sum. So if you can split up the money later again, this is what you want to go for. But if you can't, that's the assumption. Then you have a clear trade-off between gains to yourself at the expense of somebody else, right? And the same here. And then if you play this a number of times, you can find different characteristics of people. The way this is normally visualized is as a circle, right? Where you have different payoffs at different points. And you can sort of, by the angle that you would measure on the payoffs to yourself and to your others, you can start classifying people as either individualistic or altruistic, or the sadomasochists are masochists are there as well. If you do this for a sample of people, you find that people are actually relatively pro-social, and that is perhaps better seen. Here. If you sort of play for windfalls, then a lot of people go for not the maximize your own well-being, but actually go for a more social attitude. That's what you see here. Still a lot of individualists. The other types of people are actually much more rarely observed. Now, in your standard dictator game, as I said, this is played against an unknown other. You can, of course, also play this against somebody of a type, right? You cannot play it against an identified other because you don't know the relationship between the two. It would be impolite to ask. But you can play it against a type. You can let people play against males and females, not a big difference. But you can also let them play against the very young or the very old. And there you see that when we are confronted with a young child, or we are confronted with an old geezer, then we tend to be much more altruistic, much more pro-social than if we are confronted with somebody of middle age. Some people find interesting. The bigger question, as I said, is what is the best income distribution in the population? And if we're talking about issues like climate change, it's not about we have a windfall and how to divide this. we win a prize and who should get the biggest share of the prize. That is not what climate change is about, right? Climate change is about we are confronted with a distribution of impact that is very uneven, and what do we make of that? And we know that vulnerable people that are already poor are much more vulnerable. So we would see a worsening of the income distribution because of climate change. Do we care about that, and how much do we care? The way this is answered in the literature is through so-called choice experiments with a leaky bucket, and I'll explain to you the leaky bucket right away. So you ask people, which of these income distributions do you prefer? Right? And of course you can make them as big as you want, you can make the choice as long as you want, but you're just annoying your interviewees, right? So in the top one, Mark earns 60, Ben 44, Charles 33, and then we take away 2,000 from Mark and we give Charles 1,000. So half of the income transfer leaks. So that is leaks away. So that is why this is called a leaky bucket. And some people refer it to as Okун's leaky bucket because Okun was the first to suggest this. So if we move down, what we find is a population that is more egalitarian but poorer. And here it is less egalitarian but on average richer. So there is a clear trade-off. If we just ask more egalitarian but equally rich, then there is not much of a choice for most people. You can do that, and then the question is how do you interpret that? The standard way of doing this is the so-called Bergson Samuelson. So this was first invented by Bergson in 1938, and then for a long time everybody thought that Samuelson had invented it, and then some people actually started reading the literature properly and discovered that whatever Samuelson was saying had been said 20 years prior by Bergson, and since then it's become Bergson Samuelson, where we say that the welfare function W is essentially a generalized average of the utility, right? Where we take the utility of person I is consumption Ci, we take the utility of that, we raise the thing to the power 1 minus omega, and then of course we have to put 1 minus omega in front as well, and that is what we call our Bergson utility welfare function. And of course if omega is 0, then we are inequity neutral and we're back in Bentham land, right? We just have a Benthamite maximize the greatest good for the greatest number type of utility function, right? Or welfare function. Under this assumption there is no distinction between risk and inequity aversion, right? Why is that? Well, this is our welfare function. Let's assume that we have a CRA utility function. So UC is C 1 minus eta over 1 minus eta. Work that through, and what we have is that our welfare function is really this complicated thing here, and then C to the power 1 minus eta minus omega plus eta omega. So if we are just expressing preferences over different consumption levels, which is what we do because we cannot observe utility, right? We cannot observe happiness. Then you cannot say whether this is due to the curvature of the utility function or due to the curvature of the welfare function, because they just add up additively and therefore cannot be separated empirically. A defining characteristic of Bergson Samuelson welfare function is that if we multiply everybody's income by 2, we doubles everybody's income, then nothing much changes. Our trade-offs are only about relative income, but we're not saying that income inequality is more important for poor populations than for rich populations. That just doesn't show. The 2 just ends up in front, just becomes a constant, and as soon as you take the first partial derivative, the constant is gone, right? Or you take the first partial derivative and the relative, the constant is gone. So Bergson Samuelson does take into account inequity aversion in the sense that you worry about some people being less happy than others, but in a peculiar way. There's two big alternatives to the Bergson Samuelson, that is Sen's welfare function and Forster's welfare function. And essentially what they say is just take total consumption, but multiply your welfare function with 1 minus the Gini coefficient or 1 minus the tile coefficient. And this implies a much stronger inequity aversion than this, for reasons that are irrelevant at the moment. The peculiar thing, or the undesirable thing about this, is that again you are not sensitive to the level of income at all, because here if we multiply all these C's by 2, it just gets into the front of the equation, and your G and your T, your Gini coefficient and your tile coefficient, are by construction also insensitive to the level of income. They only look at the income distribution by construction. So these two have the same property as this one, that you are insensitive to the average income. And one way of going about this is to take inspiration from Hara, where you introduce a subsistence level of income, and you say my consumption has to exceed my subsistence level, and if you do that, and C sub bar is positive, then what you find is that you are more worried about income inequality in poor societies than you are in rich societies. And then what you need to do is do a choice experiment and estimate these two parameters. So if you do that, this is what you find, sort of a fairly polarized population. A lot of people who don't care about income distribution at all, right? Whose inequality parameter, the omega I just showed you, is close to 0. There's a lot of people who think this is terribly important. And then there's a group in the middle who say it is a little bit important. And then to the question, do people care more about the income distribution for a poorer population than for a richer population? The answer is perhaps a bit surprising. 2/3 say this should not matter, right? Bergson Samuelson or Forster or Sen were correct. There are also a good few people who argue, as I would argue, that income inequality is more important as societies get poorer, and those are the people here, and some have a very strong preference there. And then there's also a group of people, 3%, 4%, 5% or so of people actually say the opposite, that income inequality becomes less important as people grow poorer, because then you should really start emphasizing what is going on to the best in society rather than worry about the poor, wretched masses. Right? So this is a very elitist view of the income distribution. So to wrap up, you can measure these things. You should be very, very careful in how you do it, right? Because there's all sorts of other things going on all the time that sort of suggest that what you're measuring is not exactly what you're measuring. And the risk bias, the Prelat's risk bias, is of course the prime example there. But people just don't use the probabilities that you think they are using. But you can do this, and it reveals a lot about how we look at risk, how we look at time, and how we look at others. Unfortunately, a lot of this stuff sort of doesn't agree one bit with your standard for Neumann-Morgenstern utility calculus, which is on the one hand, sort of from an academic perspective, very exciting, right? Because there's all sorts of new things to be discovered. Of course, from an applied policy analyst view, it's really annoying that you can't just take your textbooks from the 50s and 60s and apply them and hope to have an answer, right? That is just not the case.